July 21st meeting of the Central Florida Astronomical Society. Let me click this little button here to say they're allowed to record me. Hopefully this is our last Zoom only meeting. I'll have some more to say about that in a few minutes when we talk about the next meeting coming up. First, we got a great program for you tonight, The Science of Star Trek by Dr. Erin Macdonald. I'm very excited. I think we may have a few people who are interested. Even if you're not you're a Star Wars, not a Star Trek fan, it's still very interesting to see, to talk about the science of science fiction in media today. So it's pretty cool. When she's done, we'll have a showcase of member astro photos. And John Pinto is going to talk about what time is it, calculating star time. Mauricio and Eric Hoin also, they did a outreach event with some Boy Scouts, and so they're going to report on that for us. If you'll allow, I'll spend just a minute on the moon and several minutes on the sun from Eric Hoin as well. Just a few reminders in club business. The new website is live. I know I've been pounding that in the horse, like a dead horse. But as the man on TV says, but wait, there's more. We also have a new QR code that we're going to be using in the future to help people find the website very easily. Anybody with a smartphone can put their camera on this little QR code and it'll take them straight to the website. We think this will be really great at outreach events. We'll probably still do pamphlets and things like that, but most people have a smartphone and they can very quickly pull up our website. And this is a great way to very quickly get people in contact with things that are going on CFAS. Also, one more reminder, the official member CFAS communications is through our Groups.io group. We had a big membership surge recently. Great. Thank you people for who've recently signed up. If you haven't, now's the time. This is how we are going to disseminate official news. We'll also try to cross-post on Twitter and Facebook and those things, but this will be our primary way of letting people know what's going on. One of the things we need to let people know about is, of course, there's no meeting in August. This is our CFAS tradition. In the summertime, things slow down, and we've always skipped the month of August, and we can't find a good reason not to do it again this year. So there'll be no general meeting in August. The board will be meeting in August, though, because we've got to plan the September meeting. The September meeting we're very excited about. We're all very excited about the end of these days and getting back to in-person meetings at the college. This, of course, is still tentative. We are relying on the college's current plan, which is to open up for in-person meeting in September. Anything can happen. There's all kinds of variants. The apes could start talking, but as far as we know, we're on track to meet in September. We will send out some communications via Groups.io about that meeting ahead of time. Some exciting things. We do plan to have a star party on September 11th, which is after the meeting, where we can get together and do some observing, hopefully at the college. We may spring for some extra cookies and some door prizes for the September meeting, but we'll also have some guidance. I don't know at this time what the college's guidance is going to be on masks, and we will adhere to what the college's guidance is on that, and we will let you know and communicate that to you. Definitely through Groups.io and probably through Facebook as well. Most likely, we're not, as a club, going to institute anything more stringent than what the college is imposing for on-site meetings. We do know that some people are dying to get back together, and we do know that there are people who are still nervous about getting together, and that's fine. We do plan to broadcast the meeting, and we still have to work out some technical details, but we'll probably do a combo where you can also join via Zoom for the meeting, but we will be able to get together in person as well for the people who are comfortable doing that. Also, I just at the last minute, I thought I would throw in just sort of a public service announcement about vaccinations. If you are not vaccinated yet, I am not going to tell you that you should get vaccinated. The reason is I am a software engineer. I'm very accomplished in my field. I'm an amateur astronomer, which means I should be somewhat scientific. But you know what I'm not? I'm not a doctor, and I'm not your doctor. And I hope that if you're not vaccinated, that you've made an informed decision not to be vaccinated. I know that there are good reasons not to be vaccinated. And if you have a good reason for not being vaccinated, I'm going to tell you something else many people won't tell you. It's none of my business, and it's none of CFAS's business why you can't be vaccinated. But I just hope that you've made that decision by talking to an actual healthcare professional, not somebody on YouTube, not somebody on your favorite news channel, not somebody on Facebook, but an actual healthcare professional. I have a doctor. I trust that doctor with my life. And I talked to my doctor about it, and we made that decision together. It's a very privileged thing to say, of course, talk to your doctor. Everybody doesn't have a doctor. That's fine. Talk to your pharmacist, talk to a pharmacist. Every grocery store, every Target and Walmart has a pharmacy. Go talk to an actual medical professional, and they may tell you that vaccination is not right for you. It could happen. Like I said, I have people in my own family who can't be vaccinated for reasons that are none of your business, and it's not my business either. But I just hope, from the bottom of my heart, that if you're not vaccinated, you have made an informed decision, not a decision that was sold to you or marketed to you, or politicized to you one way or another. And that's all I'm going to say about that. And so again, there's no general meeting in August, but watch for announcements about our big September get back together. I'm very excited about that. Everybody on the board is as well, and I know many of our members are as well. And that is all the boring club business I'm going to talk about. It's time to get this show on the road. Trisha, are you in a good place to talk, or should I talk about our?
I am parked.
All right, then take it away. I'm going to stop sharing, and Erin can take over whenever she likes. And Trisha,
okay. Hopefully everybody can hear me. Okay. So I'm going to go ahead and introduce Dr. Erin Macdonald for y'all, and then have her take over. So a little bit background of Erin. So Erin is an astrophysicist, aerospace engineer, and a science fiction consultant. She hosts the YouTube channel Dr. Erin Explains the Universe, and teaches STEM through popular culture and consults with science fiction creators. She earned her bachelor's degree in astrophysics and mathematics at the University of Colorado Boulder, and her Ph.D. at the University of Glasgow, where she concentrated in general relativity, because why not, right? She did her postdoctoral work with the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, collaboration as part of an attempt to detect gravitational waves from the Crab pulsar. She also did postdoctoral work at Cardiff University, still with LIGO, where she was the first female researcher in her department. Congratulations. During this period, she became involved with Actors Workshop in Cardiff, which she credits with helping her efforts at science communication. She also began teaching at a local community college, and eventually found work analyzing data in the aerospace industry. In late 2019, McDonald became a science consultant for Star Trek. How amazing is that? Cue applause. That's why she's here. Her talk, The Science of Star Trek. Thank you again for coming on such short notice, and thank you to Frank Kane for making the Star Trek connection. And I will now hand it over to you, Dr. McDonald, from tachyons to warp drives.
Yay! Thank you, Trisha, for the kind introduction, and thank you for having me as well. Frank made the connection because we were on the Star Trek cruise together in March 2020, which is a whole other story to share sometime. But I just want to make sure everyone can see the single slide and everyone can hear me okay so far. Then I'll take it from there. I shall take silence. Good. All right.
Oh, we hear you loud and clear.
Okay, good. So yeah, thank you for the introduction, especially because this was last minute, so people can have a little bit of more of a background into me and what I do. I will probably save questions for the end, and you can ask me anything about working for Star Trek, what my career was like, what I just talked about, any nitty-gritty Star Trek stuff, or any sort of science. I'm more than happy to talk about. I will have to leave though at the top of the hour, so I will abandon you all. But while it has been a difficult year and a half for many of us, I will say one of the greatest things has been me being able to connect with great astronomy societies all over the country. And so I am beaming into you from Los Angeles right now, thanks to the power of technology. And with that, I am going to kick things off with a little clip that is near and dear to my heart that we're going to break the science down. Ooh, let me actually control this.
That is a great story.
Quite amusing, Dr. Hawking. You see, Sir Isaac, the joke depends on an understanding of the relativistic curvature of space-time. If two non-inertial reference frames are in relative motion...
Do not patronize me, sir. I invented physics.
We love that, and that joke is hilarious. Now, I recognize there's going to be a lot of people in this audience who are familiar with things I'm going to talk about. I'm going to be sharing some sort of astronomy, some astrophysics, and tying it all to Star Trek. So if I'm on a topic that you know everything about, then just tune me out for a little while, or just think of your favorite Star Trek episode. But for the majority of what I'm going to discuss, we really have to understand what space-time is. Now, space-time was first conceptualized in the 1800s by mathematicians primarily, who started thinking of our universe as a four-dimensional fabric, 3 dimensions of which are space, forward, back, left, right, up and down, that we can control, and a 4th dimension, which is time, that we have no control over. We move forward at 1 second per second. And they played with this from a mathematical standpoint, but in the early 1900s, Albert Einstein took this another step further and asked the question, what would happen if we introduce mass into this fabric of space-time? And we can see, we usually use this bowling ball on a trampoline analogy, and that's what works really, really well. A lot of people sometimes struggle with that. I think people, especially who don't have a hard time thinking sort of mathematically, we're always like, but our universe is 3-dimensional and it's a 1-dimensional, or it's a 2-dimensional fabric. What's under the sheet is basically the big question. So I will say, if the bowling ball and the trampoline doesn't work great for you, I also like an analogy that is thinking more like mattress springs, where you would stick your hand in and then your hand would clump some springs together. And you can kind of picture it a little bit like this. And like I said, that's going to be kind of hard to think about when we're talking about some of the stuff we're going to talk about in this talk. But if, you know, the trampoline really trips you up, I get it. And that's no big deal. This is kind of a nice visual to help with as well. But going back to this, as I said, Einstein came up with this idea, and it was really driven by a problem that we were having at the time in astronomy. Now, we had Newton's laws of gravity, and those were working very, very well most of the time. But astronomy was getting better. And as astronomy was improving, we were noticing there was a problem with Mercury. Mercury's orbit precesses. It traces out a flower shape as it goes around the sun. That doesn't work with Newtonian gravity. Newtonian gravity requires there to be another planet that could be tugging on Mercury to be causing that precession and that movement. For the Star Trek fans out there, this is one of my favorite facts, because the planet that they used is planet Vulcan. And this is an actual star chart from the 1800s, where we can see planet Vulcan there tugging on Mercury. But because astronomy got better, we weren't seeing a planet Vulcan there. So Newton's gravity wasn't looking too good. And I know as an astronomy society, you all appreciate this. You know, as professional researchers, we can only take what the universe gives us. We can't force a star to explode in the lab. We can't have planets orbit a star in our lab. We just have to take what we see. And so it's this interplay between the theory of the physics and then what we're able to observe. So because we weren't seeing Vulcan, this was a really big trip for the future of astronomy and our understanding primarily of gravity. Now, when Einstein introduced a bowling ball onto the trampoline of space-time as the sun, you could put Mercury's orbit around it and get it to precess. Many of you have probably seen this or done this yourself at a science museum. If you can play with a gravity well, you can get the marble to precess around the middle. And so sure enough, that worked. That was a good check in the box. Einstein went woohoo and took 3 days off. But that wasn't good enough to just definitively like throw out Newtonian gravity and go with this new concept of general relativity. There's been more tests that we've needed to do. So in 1919, shortly kind of a few years after this theory was developed, they were able to observe a solar eclipse. Now, again, with Einstein's theory of the bowling ball and the trampoline, you imagine the lighter things are, the less they dip down space-time and the easier it is to move. And light, because it's massless, doesn't dip down space-time and it coasts on the surface of space-time in a straight line at a fixed speed, which is the speed of light. But when it encounters a gravitational well, it curves around. Again, thinking of a bowling ball on a trampoline, if you're to flick a marble across it, it'll get curved and go in another direction. But if you didn't see that and you're just the observer on the other side, you would think it came from a different place. So what they did to test this, and this is called gravitational lensing, in 1919, they dispatched some scientists around the world. We knew what the stars looked like when there wasn't a sun in the middle of their path. And when the solar eclipse happened, they mapped all the stars behind. And sure enough, some of them were slightly off of where we knew that they should be because their light was getting curved around the sun. So again, 2 thumbs up now for general relativity. But this concept of gravitational lensing, now that they saw it, we actually use this all the time in astronomy, particularly doing deep field stuff. You can use the massive galaxy clusters to image galaxies that are behind them. This concept of gravitational lensing, like I said, is used regularly. And in fact, we have some Hubble images where typically we'll see what's called an Einstein cross, where you just get multiple images of the same galaxy. And you know they're the same galaxy because they have the exact same spectra as they're curved around. You look at the spectrograph of them. But sometimes you get them perfectly aligned. So this is a spiral galaxy that's getting almost perfectly lensed all the way around this mass that's in the middle. But let's break down this concept of gravity wells, that dip that the bowling ball does in space-time. This is one of my favorite charts. This is from XKCD, where we look at the relative gravity wells of all of the different planets in our solar system and see how they compare to each other. And the main thing I wanted to point out on this one is a concept of what we call gravitational time dilation. And we do see this in science fiction quite a bit. This idea that when you are inside a gravity well, time moves slower for you than it does outside of the gravity well. Now, because of relativity, this is all going to give us a headache. And I know I got tons of questions about this when Interstellar came out, because they showed this as well, that if you are inside a gravity well, a few hours might pass for you, but your time is moving much slower compared to the outside. So more time will have passed outside. And it starts to give you a little bit of a headache. But the main thing to remember is that if you're in the well, you're held down. Time is going slower for you. GPS satellites are actually slightly outside of Earth's gravity well. They're further outside. And so time moves fractions of seconds faster for GPS satellites. It's fractions of nanoseconds. So it's not enough to result in some space-time sci-fi timey-wimey thing. But it is enough that if you want GPS precision, particularly for military uses, you want to know exactly where you are, not if you're around a certain area, like maybe across the street or something. And so GPS satellites are actually the only practical application we have right now of general relativity, but that's because we actually see its effects. And then, of course, Trisha mentioned in my bio that I worked in LIGO with gravitational waves. So those are always going to be close to my heart. But when we detected gravitational waves, that was the first direct detection of space-time itself. So we love that. But this idea of gravity wells, there's lots we can do with them, science fiction wise and in our practical everyday life. But let's look at how we use gravity wells in Star Trek. A great episode, one of my favorites, is The Next Generation Relics. Now, this is the one where they discover a shuttle that has crashed into a Dyson sphere, which is a whole other thing. But it has crashed into a Dyson sphere, and Scotty was held aboard and in the transporter beam. So it's not that he experienced any gravitational time dilation. It was just, they say explicitly, he got caught in the gravity well of this Dyson sphere. His shuttle did not have enough escape velocity to get out of it. So great use of a gravitational well. Then we have the Voyager episode, Blink of an Eye. This is the one where time passes for Voyager much slower than it does on the surface. Now, that means a couple minutes on Voyager results in weeks on the surface of the planet. There's a nuance to that I'm going to talk about at the end of the talk, but it still uses this neat concept of gravitational time dilation. And then, of course, when we talk about gravity wells, in the original series episode, Tomorrow is Yesterday, where we go back in time, and the one with the whales, when you warp and slingshot yourself around a sun, you go back in time. But they always talk about this idea of gravitational slingshots. Now, that is a real thing. This chart is actually the same one that's behind me here. I love it. It's a map of a path that shows every single path anything we've sent into our solar system has taken. And what you can see is that we have these gravitational slingshots as you go around different planets and moons as you travel through. And that helps you adjust your velocity, even gain some speed. And sometimes people ask like, well, but there should be conservation of momentum. And that's true. But when you have a really, really tiny spacecraft and a giant, giant planet, as it's coming in, you can think about it almost like a collision. There's a transfer of momentum. The spacecraft is going to pick up some velocity. The planet's going to lose some velocity, but relative to their masses, it has hardly any effect. And so the momentum does go down very slightly, but it doesn't affect any of the actual machinations of the orbit itself. But gravitational slingshots, talk about all the time. Now, I'm going to get into warp drive a little bit. Now, you can kind of headcanon how you can slingshot around the sun and end up going back in time. I think about it like, again, not very scientifically, but as you're going into a gravity well, time dilation is happening. And if you were to go to warp while you're going into that gravity well, time is going to get weird. That's about the best justification I have for it. Just don't ask me like how you repeat the process and then go forward in time. That's a whole other thing. But the important thing here is that in this chart specifically, I'm talking about traveling in our own solar system. And this is something I can appreciate that an astronomy society will understand, that space is very, very, very big, and it takes a long time to travel anywhere. And that means a 5-year mission is going to be kind of boring unless you can go faster than the speed of light. Here's a nice little map of the Milky Way galaxy in the Star Trek universe. Again, remember, it takes like Starfleet is on Earth. If you haven't watched Star Trek, I'm so sorry for the amount of references I'm giving you. But it does take place in the Milky Way galaxy. It is humans at Starfleet. It is not a galaxy long time ago, far, far away type situation. There is an Earth in the Star Trek universe, our Earth. But it takes place across our whole Milky Way. We talk about alpha quadrant, beta quadrant, delta quadrant, gamma quadrant, breaking up the Milky Way in this form, and then finding different ways to travel throughout it. And you're going to want to travel faster than the speed of light if you are going to explore our galaxy. So the first one I actually want to talk about, not so much warp drive is what I'll come to, but I want to talk first about wormholes, because wormholes theoretically are a thing. Mathematics of general relativity and how our universe is laid out doesn't, like, the math works for there to be wormholes. We just haven't detected any. They're also known as Einstein-Rosen bridges. And a nice way of thinking about it is if you were to take like toilet paper, for example, crumple it all up, and then lay it out flat, but really haphazardly. Like, you'd have parts where it's folded over itself. You've had parts where there's bumps and ridges. And what a wormhole is thinking like, all right, normally at the speed of light, I would have to go over all of those folds and bends. But a wormhole would be like if you staple it or if you just punch your way through and you're able to shortcut that. Again, mathematically, with the fabric of space-time, wormholes are okay. We've just never detected any. And they kind of have a similar topology to black holes. So just lots more to explore. And as a theoretical astrophysicist who loves science fiction, I'm all about wormholes. But we see them a lot in Star Trek for obvious reasons. A great episode that I would highly recommend is an episode called Eye of the Needle in Voyager. It's one of the first episodes in season 1. I think it's like episode 5 or 6. But the Voyager spacecraft is caught in the Delta Quadrant. That's the first episode. They throw them across the Delta Quadrant. They're trying to find their way home. They find a microscopic wormhole, a tiny wormhole, that is connected to the alpha quadrant, to home. They're able to communicate a message through it, and they're able to contact a Romulan on the other side who is being difficult and Romulan-y, and they find a way to transport him through the wormhole onto their ship. But something's off, and what they discover is not only does the wormhole connect 2 points in space, but it also connects 2 points in time. And I think that's something that we miss a lot in science fiction when we talk about wormholes as a method of faster than light travel. You have to remember that you're connecting 2 points in space and time. And so it's important to think about. It is possible to sort of maintain that, but you just have to factor in all 4 dimensions when you're thinking about a wormhole. Again, though, great episode, highly recommended. Another one is like a weird 2-parter. One is The Next Generation, The Price. It's where they find the Barzen wormhole, which is this wormhole that's like super unstable and bouncing all over the place. And then some Ferengis like are all difficult and they go through it. And then in Voyager later, Voyager discovers the planet in the Delta Quadrant that the Ferengis got to. Very funny, all good things. And then of course, there's a freaking series based around a wormhole. So Deep Space Nine is set at a space station that sits on the edge of a wormhole that connects the Alpha Quadrant to the Gamma Quadrant, where bad, scary things happen, and the Dominion War, and lots of excellent television comes from it. But all of these are ways that we can travel faster than the speed of light, because we're connecting 2 points in space-time. Also, I do want to warn people, I am going to mention some stuff from Star Trek Discovery. There's going to be a little bit of spoileriness to it, but I'm going to stay mostly away from it. But between seasons 2 and 3, Discovery goes through a wormhole. Now, Discovery in seasons 1 and 2 were set way in the past in the Star Trek realm. But this wormhole at the end of season 2 flung them 900 years into the future. And one cool thing is that Burnham went through before them. She got through on the other side in a different location in space and time. And then Discovery didn't show up until a year later because of the gravitational time dilation that they experienced coming out of the wormhole. We love it. Love to see it. Okay. Now warp drive. I mean, when we say we're going to talk about physics in Star Trek, warp drive is like the first thing everyone thinks about, and it's my favorite thing to think about. It was actually the first sort of science fiction thing that I scienced when I was procrastinating my dissertation. I was like, I have the skills now to calculate how warp drive works. But conceptually, it's great. The idea behind warp drive is that nothing on the surface of space-time can go faster than the speed of light. Remember, I said up top, when we think about that sheet, you think about a bowling ball that's on the sheet, and then that bowling ball is going to be moving. And the lighter it is, the easier it is to move, but it's always going to be dipping space-time slightly. And then you get to flat space-time where no mass travels at a fixed speed, which is the speed of light. But nothing in that says that space-time itself can't go faster than the speed of light. That's the concept behind warp drive. If you're able to build a bubble of space-time around your ship and have that propel you faster than the speed of light, that's how warp drive works. Now, the cool thing about this is, like, conceptually, it's great. It's like, oh, we have this magical fix for how warp drive works. But they imposed some rules on this. So looking at this chart again, Voyager was flung into the Delta Quadrant, and they were flung about 75,000 light years from home. They're not going to get home immediately because they have to travel at warp. Warp requires some energy, which I'll get into. But it's going to take time. And we have these like warp factor 1, 2, 3. People have tried to ascribe some speeds to it, but there's been a lot of randomness over the 55 years that Star Trek has been around. So I wouldn't pay too much attention to it. But the concept of warp factors just has to do with the fact, like, you build a bubble of space-time around your ship. You want to go faster than that. You could build another bubble around it. That will take you from like warp factor 1 to warp factor 2, and you're going to accelerate exponentially and continue to go faster and faster. Again, math behind this is great. You keep the space-time where your ship is constant, and so you're still not breaking physics at all, and you compress space-time in front of your ship and extend it in the back, and that's what propels you. Some of you may have heard of the Alcubierre drive. This has been an effort to actually formalize the mathematics of how a warp bubble will work. There's a few nuances to this that I really thoroughly love. Now, I mentioned when you introduce mass to space-time is how you dip it. But if you want to bend and fold space-time and you don't have mass, you could go to Einstein's other theory, which is mass energy equivalence, or E equals mc squared, where you could have an equivalent amount of energy to bend space-time to make it do things like this, like what you wanted to. But when they first did the calculations for this sort of mathematical construct to figure out how much energy it would take to bend space-time like this, the result was all the energy that's ever existed. It's not ideal. I do think it's been a few years since I've seen any updated calculations, but the last time I saw, they had got the energy equivalent of a semi-truck. So you took the mass of a semi-truck and broke it down to its energy. You could build a warp bubble with that. But bear in mind, like the hydrogen bomb is a teaspoon of matter converted to energy. So I like to joke that that's why Zephram Cochrane, who invented warp drive, drinks as much as he does, because I wouldn't want to strap myself to that one either. But anyway, the concept behind warp drive mathematically is really sound, and we like it a lot. Now, because a lot of scientists, some of you guys as well as myself, got into astronomy and science because of Star Trek. Once NASA got their hands on this, they commissioned some artists to think about what that ship would look like, and it's the Enterprise. I mean, you can't get around that, but we love it. All right. Next thing I'm going to talk about is dilithium. Now, dilithium is one of those things that has been around since 1966, since the first Star Trek episodes. And most people, up front, dilithium in the Star Trek realm is fictional. They talk about dilithium crystals. None of that exists. Lithium exists. You can make some molecule of it, but you're not going to get a crystalline compound out of dilithium. So just up front, all that I'm talking about is the fictional matter that is called dilithium in Star Trek. Now, most people, and this is okay, even hardened Star Trek fans, think of dilithium as the fuel for the warp drive. They think that because when dilithium crystals aren't available, the warp drive goes down. If you were to say that, Scotty would give you this look. But really, what it is it's like a regulator for matter-antimatter collisions. Recall I said, if you want to build a warp bubble, you need a lot of energy. That energy in Star Trek comes from matter-antimatter collisions. That's what's going on in the warp bubble. Now we can, and this is a physics thing, right? You have electrons and positrons, that's matter and antimatter. When they meet, they annihilate each other and turn into gamma rays, which is high energy. And then we can get even more complicated processes that happen with other matter and antimatter. But really what's going on is the warp core in starship engines in Star Trek are regulating matter-antimatter collisions to create a lot of energy to then pipe that through and build the warp bubble around your ship. However, that's a lot of really scary stuff that's happening. And like in a nuclear power plant where we have control rods that control the processes that are happening to keep them from getting into a positive feedback loop, that's what dilithium does. So dilithium really is a regulator for matter-antimatter processes. And if the dilithium breaks or cracks or something, or you run out, then that matter-antimatter process is going to go out of control. You're going to get these positive feedback loops. So I worked on season 3 of Discovery, which was rooted in this season-long arc where they had something that was called the burn. And what happened was that a bunch of dilithium, any sort of active dilithium, destabilized and caused warp drives to explode. I came up with a lot of science behind dilithium that didn't necessarily make it into the dialogue, but that we were able to science, where we talked about this idea that maybe in the future and in Star Trek, they've interacted with dark matter more than we have here. And what if dark matter had some sort of, I called them complex gauge bosons. A gauge boson is a force-carrying particle, But what if there was a force-carrying particle that existed in the complex plane, which could also be thought of as subspace or like imaginary numbers? Because math, if there are any mathematicians in the audience, once you get into the complex realm, like it's really fun. And there's a lot of cool stuff you can do with it. And I like to think of this area outside of our trampoline as sort of the complex plane. So technologically, what if we discovered a complex gauge boson that could exist in the complex plane? And maybe this is what makes dilithium, again, a fictional particle, effective for warp drives. It's all fine. It's all in my head. If you want to learn more, and you have seen the science of, and you have seen season 3 of Discovery, myself and Professor Mohammed Noor from Durham University, he was also a science consultant for season 3 of Discovery. He did the biology behind what happened, which I won't say because I don't want to spoil it, but I did all the sort of dilithium science. This was a little bit of a preview to it. So you can check out this article. It's still online on StarTrek.com that we wrote getting into the science behind all of this stuff, but I think it's fun. All right, another must talk about when you talk about Star Trek technology, even if you're not a Star Trek fan, you've heard the phrase, beam me up, Scotty. This idea that we can have transporters that break our particles down and rebuild you somewhere else. Now, the issue is, there's a few issues, but the first one is that even within Star Trek canon, they kind of contradict itself in how the transporter works. So in one aspect, you have this idea that the transporter, when you go in, breaks you down to your subatomic particles and then moves those particles somewhere else and rebuilds you. This is the way Hoshi explains it in Enterprise Vanishing Point when she's like, I ain't going in that transporter. That's crazy. That's a death machine. She talks about breaking all the particles down, moving them, and rebuilding you. Contradictorily, another way you could think of the transporters working is breaking down all your subatomic particles, mapping out where they are, sending that information as data, not the android, but as data, and then using that to rebuild you out of other material. And that's how you could get like duplicate people by accident. And like I said, Star Trek has, these are 2 examples, but like Star Trek has many examples that could be both of these things. And it's not definitively yet come down one way or the other on that. But trying to figure it out, I was like trying to kind of science how the transporter could do that. Maybe, you know, if it's particles versus light, they'd be slightly slower than the speed of light. If I wanted to travel from Starfleet Academy to Cisco's Creole Kitchen in New Orleans, that's about 2,000 miles, which is further than low Earth orbit, which is what they normally transport from. Regardless, it's still about 0.1 seconds to make that trip at the speed of light or at slightly less than the speed of light. So that doesn't really definitively say one way or the other. Because I thought maybe if it took longer, depending on the size of the particles, we could come up with an answer, but we can't, and that's fine. But it doesn't matter because it's not going to work anyway because of Heisenberg's uncertainty principle. This is the only equation I'll show you. For those of you who may not have come across this before, the delta is the change in the triangle. X is your position. P is your momentum, which you can think of your velocity. And then that h bar over 2 is just a number. It's just a constant. There's nothing fancy about that. And what this is saying is the more you know about where something is, that error on your position, that delta means your error, the better you get, the smaller that gets, the knowledge of your velocity, how fast you're going, is going to have to increase because they multiply together and there's a limit to what they can be, that they always have to be greater than. So you're never going to get your knowledge to 0 because that would contradict this. And the less you know, or the more you know about one, the less you know about the other. The great joke for this is that a cop pulls over Heisenberg and says, "Sir, do you know how fast you're going?" He says, "Nope, but I know exactly where I am." And the cop says, "Well, you were going 70 miles an hour." And he says, "Great, now I'm lost." So that's how Heisenberg's uncertainty principle works. But that's why transporters couldn't work, because you would have to know exactly where every single particle is if you wanted to transport them and map them all out. But Star Trek did a brilliant thing with this. They invented the Heisenberg compensator. This is a piece of technology inside the transporter that We don't know how it works, but it compensates for Heisenberg. And so we're good with that. It's a perfect example of like acknowledging that we're breaking physics and accepting that and folding that into our story without actually having to solve it. And the joke around the Star Trek offices is, you know, Dr. Erin, how does the Heisenberg compensator work? Say, it works very well. Thanks for asking. That's what we stick with. Now, some people may have seen in the news like about 5-6 years ago that I think Chinese scientists successfully transported a particle that was a little bit misleading. Try to contain your amazement. What it really was is that they were able to sustain quantum entanglement between two particles from the ground to the surface. Looks pretty good, but more experiments have to be done for that. But I just wanted to clarify, like in terms of where we are from transporter, we're still a ways off and we're never going to get to people because of the uncertainty principle. Now, just a really quick fun one, photon torpedoes. I get asked about these ones a lot. Photon is the name of a light particle. So that means faster than the speed of light. So how could a photon torpedo look like that? And we could see it moving through space. An explanation I have for this is a little bit dark, but if you think about that, not necessarily being a packet of light that is being sent from the Enterprise to an enemy vessel, but rather like literally a torpedo that when it gets to the enemy vessel explodes and releases high energy light that does a lot of damage. That's also a nuclear bomb. So that kind of implies that photon torpedoes are just nukes that were flying everywhere. So that's where it gets a little bit dark, but we'll go with it. It's fine. I just think of it's a way to transport photons. It's a way to take photons from the ship, send them there, and then do damage once they're actually there. Cloaking devices. These have been around in Star Trek technology since the beginning as well. This has been a fun one for scientists. A lot of scientists have done research into ways to cloak or go invisible. Here's some research that's been done into sort of chameleon-like science, where you could wear a jacket that maps what's behind you and then project it in front of you. Again, not great. This kind of looks like crummy green screen technology. You know, we've all had the virtual backgrounds and everything this year. It looks better than this, but this is like actually the fabric itself that's emitting this, not a trick of camera play. So that's pretty cool. There's also been some research done up in Rochester to optical benches and how you can bend light in a way to make an entire region inaccessible to the eye. So this works really well. It's just playing with light beams and magnifying and bending them in a way that like nothing here can be seen, but only if you're like looking specifically down one side. You move over to the side, you're like, oh, that's all there. So that doesn't work great either. But the technology that we talk about with cloaking devices in Star Trek, really what it means is it's like not seen in the electromagnetic spectrum. We know as astronomers, we observe things in space either through emission or reflection. And so when we're looking at a star, that's the light it's emitting. We're looking at like a moon or a planet, that's the light that's being reflected off of it. They also glow a little bit just from the heat. We get black body radiation. So theoretically, a cloaking device would like hide all of that. And that's how they talk about it in the first thing that we see, cloaking devices in the original series episode, Balance of Terror. Again, classic episode. If you haven't seen this one, very, very good. But this idea that you mask your entire electromagnetic presence. We also look at cloaking devices in the Next Generation, the Pegasus, where they're trying to figure out how to detect them. And then there's a fun one in Voyager, in Distant Origin, where a species manages to cloak themselves from being detected, but not from space, but they cloak themselves in time. So they're always slightly offset of the time on the ship. And that's kind of a cool way of thinking about it. Now, again, if we think about a cloaked device, there's a big issue here. It's going to heat up. It's not emitting any electromagnetic radiation, which means it's not emitting any heat that it's giving off is still being trapped. So it's going to get real hot real fast. So you don't want to stay cloaked for very long. But while you are cloaked, you do have a gravitational presence. And this is something they addressed in season 1 of Discovery that might be my favorite Star Trek science moment. I cannot take credit for this, but it's brilliant. they basically said, all right, we want to detect cloaked Klingon ships. They're bending gravity. Let's use gravitational lensing and triangulate their position. So what they do is they look at the position of the stars in their field of view. They jump slightly, look at the stars in that field of view, jump again, look at the stars, and then see how the positions of the stars slightly move at a microscopic level and be able to detect the presence of a gravitational object there. So good, so brilliant. I love it. Really quick, just a few more things. Planetary scanning. This is something that we do and see regularly now. You know, in the 60s, it wasn't impossible, but you got to remember this was 1966. I mean, we're just on the cusp of like launching satellites. We've started sending humans into space, but we haven't sent humans to the moon yet. And so the idea of building out these planetary scans now is just something that is regular technology that we use every single day, particularly with polar satellites that we use for weather, where they just go around the poles and then the Earth rotates underneath them and they build out those strips and those maps as they go. Another piece of technology that isn't terribly far off is tricorders. Tricorders are something that Star Trek has promised that sounds great, and a lot of people have tried to put effort into. Particularly, there was the Qualcomm X Prize from a few years ago where they awarded, it was like $1 million to be able to observe 5 life signs. So things like blood pressure, temperature, heart rate, and then diagnose something like 13 diseases that someone can have without contact. So like the tricorder just scans, it's non-invasive. The reason I say, and someone won this, they were able to build that technology. Now it's very expensive and huge, not a handheld device, but they were able to do it. And I think particularly with the situation our world is in right now with a pandemic that is very easily transmissible, the idea of having non-invasive or non-contact medicine is going to continue to be pushed further and further. And it's that necessity bears, innovation. And so I think personally, like tricorders are going to continue to be pursued and will not be far off of them. I mean, I can look at my heart rate and my oxidation on the sensor on my phone. So we're right on that verge of that Star Trek dream right there. Inertial dampeners are just something fun that I love because you have to think about that phrase for a second, right? Inertial dampeners. Your seatbelt is an inertial dampener. You're welcome. That's your, dad mom joke for forever. You have to engage your inertial dampeners is put your seatbelts on, kids. And that's because inertia is the desire for an object in motion to stay in motion or an object at rest to stay at rest. And a change to that is going to be met with a force. Your body's going to want to keep moving, so you need to hold yourself back by having a seatbelt. Or for any, probably not Central Florida, but anyone who grew up in a place where there's a lot of snow, you need to wipe the snow off the top of your car because then it creates a frictionless barrier as your car heats up. And when you come to a stop, the snow does not and ends up on your windshield. And fun. I grew up in Colorado, so I know that well. But how inertial dampeners in Star Trek work? You could think of a few things. Really, it's just some sort of compensator for when your ship is changing speeds. And when it's not able to do that is when it's really abrupt. It's like when your seatbelt locks, right? That's a really abrupt motion that you then feel. It doesn't sort of slowly give. And that's kind of how the inertial dampeners react in Star Trek. Now, there's one sort of, I think one last major thing that I wanted to mention, tachyons.
Each ship will send out an active tachyon beam to the other blockading ships. Now, in theory, any cloaked vessel that attempts to pass between our ships must cross that beam and be detected.
Yeah, tachyons. We love tachyons, otherwise known as warp particles. So the great thing about tachyons is they're used all the time in Star Trek. People associate tachyons with Star Trek all the time. But the fun thing is tachyons are actually not born out of Star Trek. They are an actual theoretical particle. They have never been detected, but they are a theoretical particle that people are trying to figure out how they could detect. Now, what they are is, I'm going to use some very simplistic terms. I sometimes have people call me out on this. I realize it's a complex thing to talk about. But the idea that you can think of with tachyons is that they have like negative mass or negative energy. So instead of dipping space-time down, they invert it. However many detail you want to get into it, because the mathematics of tachyons is like a freaking nightmare and not at all appropriate for a short presentation to an astronomy society. The tachyons are inverted space-time. And so that means they always travel faster than the speed of light, and they invert space-time. So all those gravity wells that we talked about earlier at the top of this presentation, those are now opposite. Which, if you recall, if you're paying very close attention to the episode Blink of an Eye, this is the Voyager one, where time passes slower on Voyager than it does on the planet itself. That's an inverted gravity well. It should be the opposite of that. And indeed, in this episode, they mentioned that this planet has a tachyon core. Which would mean it has an inverted gravity well, which would mean that that gravitational time dilation is appropriate. Then the next question you're going to ask is like, but then how does gravity work on the planet? And I'm just not going to answer that question because I don't have an answer for it. But the tricky thing about tachyons, I had one equation, I've got one graph. I'm not going to get that much into this, but the idea that when an event happens, let's say an event A, that information propagates through space and time. And because of the physics we know, it can never propagate faster than the speed of light. So if you think about the whole butterfly flapping its wings story, that flapping the wings, any information that comes from that, any sort of nonlinear chaos theory that you want to talk about, is still never going to happen faster than the speed of light. But tachyons break that whole thing. So that light cone, that's the speed of light limit. Anything that happens within there could have had enough time to propagate. Anything out of there would be faster than the speed of light. But tachyons always travel outside of that light cone. So our concept of causality is like thrown out the window with tachyons, which works great for science fiction because, like I said, we see tachyons in Star Trek all the time. The clip that I showed earlier talking about building a tachyon web, because your ship is going faster than the speed of light, it's going to leave residual tachyons behind. Think about these sort of like waves, these ripples that are left behind from traveling faster than the speed of light outside of that light cone would result in residual tachyons. There's also a great episode, Deep Space Nine Explorers. Benjamin Sisko tries to build an ancient Bajoran light sail that, according to the Bajoran legend, took off to do deep space exploration and then disappeared and theoretically ended up on a planet like light years away, which couldn't have happened because this was sublight technology. But when he tries to recreate this path that they took, they encounter a tachyon eddy that then flings them faster than light to a star system many light years away. Also, spoiler alert, Voyager in the final episode in Endgame, Admiral Janeway from the future travels back in time through a wormhole to talk to Captain Janeway, to get her ship home faster. They detect the presence of Admiral Janeway and time travel because of a surge of tachyons that come through the wormhole. And then in Enterprise Cold Front, they detect that Agent Daniels is a temporal agent from the future due to high abundance of tachyons on the ship. So again, all the ways I've talked about, they're all very different ways of talking about tachyons, but it's all technically correct. Anything that's faster than light, anything time travel-y that breaks causality, any faster than light travel, all of that would result in, however that would happen, tachyons. But I want to talk about this for a second because I talked about it being an ancient Bajoran light sail. This is so great because all it is this idea that you build this foil, this sail, and then it uses solar wind to hit the sail and accelerate that. And I'm sure many of you are aware, this is a technology that we now have. Thanks to the Planetary Society, they were able to declare in orbit a Light Sail 2, which is the first object in orbit to successfully change its orbit solely due to using solar sail technology. So yay, good times. All right, with that, that's the end of my talk. I will answer questions for about 5 minutes or so. If you want to hear more of this, I did some videos for StarTrek.com. So if you just look up StarTrek.com and Erin or Dr. Erin, I have one on wormholes, I have one on transporters, and I have one on warp drive. It'll be a slightly extended with lots more clips from Star Trek version of the talk that I just gave. But with that, I would be happy to take questions.
If anybody wants to put their questions in the Q&A, let's see. Do we have any questions?
Looks like there's a couple in Q&A, Tricia, from John and one from Todd.
All right. I can read them. It looks like John asked, assuming one actually had antimatter power generation like in the show, does the math work out for creating a warp bubble? I've heard there's not enough energy in the universe to sustain that. Yeah, right now with our current method of the amount of energy you get from matter-antimatter collisions that we've seen like at CERN, that's one of the major experiments they do at CERN is colliding matter and antimatter. You don't get enough energy out of that to create a warp bubble, but I would say the thing that's going to get us to warp drive soonest is going to be any energy generation, whether that's through matter, antimatter, whether that's through some other technology that we're able to discover. If we're able to generate a whole lot of energy with very little, without it being, unphysical, then that will take us closer to warp drive. And then you asked about the burn seems similar to the omega particles going bad in Voyager. Did we think about linking the two at all? No, because they had already established the dilithium aspect and what they wanted that to be. And again, I'll avoid saying what the cause of that ends up being, but I can't say it's not omega particles. They had already built that all in before they brought me in to help with the science. So they had already kind of decided. So if that had been discussed earlier, I'm not sure, but they had sort of landed on what the cause of the burn was and the link to dilithium before I was brought on to help with that. And then Todd asked about interstellar, wondering something about black holes. From a perspective outside the event horizon, time is observed to slow down as another object approaches the event horizon. At the event horizon, time stops. So from our position for outside the event horizon, everything is frozen in time, which means that from our perspective, there's no singularities inside black holes because they haven't happened yet. Is this understanding correct? Yes. This is all the relativity thing that will result in a lot of crying in the shower because it's like hard to wrap our head around because it's all relative to the observer. So for us, there doesn't appear to be a singularity because the stuff has been frozen in time. And now the reason it's frozen in time has to do with this concept of escape velocity, right? That information, again, as we talked about, can only travel at maximum the speed of light. So anything that's happening there is trying to crawl out, but it's going to reach a point where it is falling and falling and falling. And once that escape velocity reaches the speed of light, then that's it. And that's the limit. That's all we'll be able to see. Anything that happens beyond that, we cannot see because no information can escape from there. So the black hole itself does have a singularity. And the reason that we know that was always theorized, but we do know that more definitively now, thanks to LIGO and the detection of gravitational waves from colliding black holes. So the topography of a black hole is known. It's just we're limited in the information we can get electromagnetically due to that event horizon. But thanks to gravitational waves, we can start to detect more from that. John Frank asked, what's my favorite Star Trek episode? Yay! My favorite Star Trek episode is a Voyager counterpoint from a story as well as a science perspective. They're trying to find a wormhole that keeps moving, that's unstable, to try to smuggle a species that are being tracked for being telepathic out of this bad region of space. And there's a lot of intrigue and a lot of who done it, who's on what side, because one guy sort of betrays the bad guys in that episode and tries to join their ship, but does he really? And the great thing for me is I was very inspired through my PhD by Captain Janeway and her fictional origin stories that she started out as a science officer, and they really try to you get to see her be a scientist in a very relatable way, trying to solve this problem about wormholes, which I really, really love. And then last one, because I only have a few seconds left. John asked, does Star Trek ever address the problem of navigation at superluminal speeds? Seems to me maps will look completely different at different destinations. Yes. Star Trek does not address that. And I don't hate it for that, because I think that that adds a layer of complication to storytelling that is like not worth it. So there's two examples of science fiction I can give you that, like, pop science fiction, television, lots of people have seen type thing, that do address this really well. One is Battlestar Galactica. So Battlestar Galactica, instead of using warp drives or wormholes, uses a concept called jump drive, which is essentially where they're here, they want to go there. They take that point in space and time, bend space time, so that point is where they are, jump, and then unbend it. But they talk about the red line. And the way the red line works is it's like, we can predict where stuff is going to be based on its proper motion, which I'm sure you're all familiar with, its motion through space. We can say, okay, if we want to travel 20 light years, that's where about all this stuff will be. But your certainty in that knowledge is going to decrease the further out you're trying to go. And you're going to reach a point where it's because of, chaos theory and nonlinear dynamics, there's going to be a point where you can't predict happily where that's going to be. And that's where they call the red line, that it's like, if you think more about government or engineering processes, you have like 95% certainty or 99% certainty that you won't, that's mission critical. That's what the red line is. And then another episode was weirdly an episode of the Voltron rebooted Netflix series. They actually have a whole plot around the fact that they miscalculated the gravitational time dilation due to their faster than light travel, and they showed up to an event one day late, which I was so thrilled to see, because you hardly ever see that. So anyway, all right, I'm going to call that there. I really appreciate everyone's questions, and thank you for having me. You can find me online at Dr. Erin Mac, DrErinMac, primarily on Twitter. And thank you again. I'll hand everything back over to you guys.
Thank you so
Thank
much.
you, Erin.
Of course.
That was
All
a
right.
great talk.
So I'm going to jump off. Live long
Okay.
and prosper. Hopefully we'll cross paths again soon. Stay safe, everyone. Bye.
Okay, that was really awesome. Now back to our own local stuff. We're going to have our first. We'll start with our astro photos from members. Anybody who is an astrophotographer or a sketcher, please send us your photos every month so that we can highlight them and let people know what everybody else is working on. And so here we are. The first one is going to be me. I got a picture of the moon and Venus the other night, handheld with an iPhone. And I was like, yeah, this is pretty cool. It's amazing what you can get with an iPhone, held real still on your car. You can do actual astrophotography. And if we were meeting in person, this is the point where Bill Castro would stand up and scream, "Hold my beer," because Bill sent in these iPhone photos, and you can see the Milky Way in these. Bill, are you around? Do you want to jump in and say anything about these photographs? Put you on the spot. Didn't know I was going to call you out. Or he's not here. I don't know. But these are pretty cool. They were 3-second exposures, handheld, resting on a deck rail. That's pretty awesome. You can do. Oh, hey, Bill, there you are.
Yeah, I just got something to unmute.
Okay.
And I just, as an iPhone 12, like everything says there, I was on vacation, and not too high in elevation. I was happy to see the Milky Way.
Mm-hmm.
And I just tried it, and then just dumb luck, it turned out. It was great. Great to see the Milky Way again, and then it was great that it came out on this my new iPhone there.
Yeah.
I can't remember whether I think the image on the right is with the 2x lens, and the image on the left is just the 1x. I think the wide field was too wide, and it got too much light on the tree. But yeah, it turned out a lot better than I thought. Just try it.
Yeah, I see Sagittarius there, the core of the summer Milky Way. That's pretty amazing. It just technology moves forward. CCD cameras 20 years ago and 25 years ago, what it took to get something. Most amateurs today can do things that are, really amazing. And I think, we're just seeing the beginning of what can be done with a handheld, with your phone. That's pretty cool. And thanks for sending that in, Bill. The weather's been lousy, but a few hardy CFAS members set their alarms and went out and got some images for us. Frank Kane with his new observatory. I think he's given up some sleep to catch some opening times. Frank, I'm going to let you talk about these next two photos. What's this that we're looking at?
Yeah, this one's M17, the Swan Nebula, also known as the Omega Nebula, and see whatever you want to see in it. But yeah, I mean, it's been pretty cloudy the past month, so whatever few hours of clear skies we have, we kind of got to take full advantage of. This is only about 3 hours of exposure time taken over 2 nights over the space of 2 weeks, because that's all I got. But, it's a good story if even if you only have a few hours, you can still get some pretty pictures. I do hope to further get some more time on this later this week if things look good at the end of the week like it should. But the trick here, and with the next one as well, is collect the hydrogen alpha data whenever you can, because that's pretty much immune to light pollution, and try to focus any oxygen during the dark times when there's no moon out, which is exactly what happened here on the Eagle Nebula M16. So again, this is only about 3.5 hours of time because it's all I could get. But the trick there, again, is to just make sure that the oxygen data is collected under the best conditions that you have available, because that's going to be more susceptible to light pollution. But yeah, that's the pillars of creation there in the middle of Hubble fame, and I'm pretty happy with that one. It's hanging up on my wall right now.
I like your treatment of the dark areas, the dusty areas. You don't. A lot of times those are all flat, and you can't see that it's actually sort of a nice opaque, smoky, like you're looking through something. And you've captured that well in both of those images.
Thank you. Yeah, I mean, it's this one's straight up SHO, but the trick is kind of to linear fit everything to oxygen. That's kind of the technique I've been using for that. So gives you some good results.
Okay. So 2 nebula in our own galaxy, and going out further. Fritz, you're our last image. If Fritz, you want to jump in, Fritz?
Sure, yeah. So definitely not new data. Processing, this is probably from 3 or 4 months ago at this point, but this is about 14 hours in LHA RGB, using that hydrogen, kind of get that red, saying, got to do something on those full moon nights. But this is, again, with the new RC10 setup, it seems to be working pretty well. Able to get some decent core detail there in the middle. Could definitely benefit from some more data. The RC10 is a little slow at f8, but maybe later on combine this with some wide field imaging and kind of bring out those outer arms.
And where are you located, Fritz? Where's this?
Yeah, so I have a little 6-foot TI home dome observatory out in Lake Nona, Moss Park area, just in my backyard. Okay. So it's about Bortle 5. And then I use the Kodak 8300 chip, so it is also a bit noisy. So combine that with the light pollution and need quite a bit of data.
Well, very nice work then, still. Okay.
Thanks.
All right, so that is the last of it. Next up is going to be John Pinto, who's going to talk to us about what time is it?
Hello, hello, everybody.
Back to you. Oh, I hear you.
Yeah.
I'll stop sharing and let you take over.
Okay. Okay. All right. So I was trying to figure out a nice name for this talk. So what time is it? And maybe that kind of goes along with the Star Trek theme of figuring out where you are in time. But I thought this would be a nice way to introduce some of the concepts that we use or that our equipment uses internally to figure out what's up in the sky. So the first thing you have to figure out is what is your local star time, or what is your local sidereal time? It's the fancy term for it. I like to just call it star time. So I'm going to show you how you could calculate it yourself. So as you are probably all familiar with, when you're sitting outside looking up in the sky, you know, in this particular, let me get an arrow here. Okay. So when you were outside looking at the sky, this is a representation of looking at Orion. You'll notice that the stars rise in the east, get higher in the south, and then go down in the west. Every star has what I'll call a coordinate that's based on time. And when one of those stars is directly south of you, its coordinate is your local star time. So again, it arches from the east, rises in the south, and sets in the west. So what we want to do is find out, you pick a time that you're going to be observing and say what is going to be directly south of me so that I know what stars are up in the sky. So how do we know what time that is? That's what we're going to do. So the first thing we have to do is take our local time that we see on our watches and convert it to coordinated universal time, which is the time that we as astronomers use to figure out what time things are on Earth. We will use our favorite Julian day number calculations to convert that to a Julian day number. And then that will tell us what the star time is over Greenwich, England. And from that, we can calculate what our local star time will be here in Florida. So again, as usual with my presentations, I try to simplify this as much as possible by assuming we're observing here in Florida, so I'm not going to show you how to do it all over the world. And I'm using some very good approximations. You know, this is not something you would use to travel the galaxy, but it's good enough for here in Florida until about 2080. And our accuracy is actually going to be pretty good. We will get to about 1/10 of a second of star time. So what do we need to know when we want to get started with this calculation? First thing is we need to know is, when do we want to do this? You know, is it going to be tomorrow at 6 o'clock in the evening? Is it going to be at midnight? Whatever. So for my example, I'm going to use make-believe August 1st. We're going to go outside, 10 p.m. Eastern Daylight Time, and we're going to do some observing. We also need to know where we are on the Earth, because that tells you what stars are going to be above your head and due south of you. So we need your latitude and longitude. Actually, we're not going to use latitude too much. In fact, probably not at all. But that's going to come into another talk we're going to do that's kind of the sequel to this one. But for this example, I'm going to use our wonderful plaza outside the Seminole State College, where we do a lot of our outreach with our telescopes. So that would be a nice location to use. So if you want to write that down, or when next time you're watching the video, that is the coordinates for that plaza. Okay. So first thing we have to do is we have to convert that local time to coordinated universal time. It all depends on whether our local time is standard time or daylight savings time. That's pretty basic. So we know August 1st, it will be daylight savings time. So to get UTC, we're going to take August 1st, 10 p.m. and add 4 hours like the little formula says up here. So actually it will be UTC August 2nd, 2 a.m. Remember, whenever you're doing this conversion, you may be changing dates. So you got to kind of be careful about that. All right, so the next thing we want to do is we want to calculate the Julian day number for midnight of that date that we just calculated. So August 2nd, 2021, what is the star time at Greenwich at midnight, 0 hours? And a lot of these techniques you're going to see were in a previous mini program I did on calculating algal minimums. You can go back and look at that if you want to see some of the background, but I'm going to go through this fairly quickly for you. So we start with what's the Julian day number for our year, the beginning of the year. And this was a formula we had looked at back then. It's pretty straightforward. And that's the number for 2021. Beginning of 2021, that was the Julian day number for 2021. The next thing we need to know is the Julian day number for August. We are in a non-leap year, so that affects our calculation. And it's basically our Julian day number for the year, plus the days into the year of August for a non-leap year, which is 212. You add the two together and you get this number. Finally, since we're talking about the 2nd of August, you have to add 2 to that. Pretty simple. And this is our Julian day number we're going to start with for the first, for August 2nd, 0 hours or midnight. At the end of this program, I put all the DIY values for all the months of the year so that you can do this calculation for any date and time that you're interested in. All right, so now we have to do the Greenwich mean sidereal time or star time at Greenwich. The first thing we have to calculate is something called the Julian century fraction. This is a new concept we haven't seen before in my previous talks. So a Julian century is 36,525 days. You probably recognize that number, right? A solar year is about 365.25 days. A century is 100 years, so you multiply that by 100, and that's why we get 36,525 days in Julian century. And what we actually need to know to calculate sidereal time, star time, is we need to know the fraction we are into the Julian century since noon, January 1st of 2000. So take our Julian day we calculated, we subtract it from the Julian day for noon of January 1st, 2000, and divide it by the Julian century number of days. So that was our Julian day number we calculated. We subtracted out, divided by 36,525. So we are actually 7,883.5 days since January 1st, 2000. And we get a fraction about 21% of the century. Okay. Now we're ready to calculate the star time. We're going to use that T to calculate it. And we're going to use this number called T0. And you'll see how why that's important. So we take our T, we multiply it by 2400, 0.051337. Add that to this 6.697374558. Multiply that out, add it together, and then subtract out all the 24-hour multiples so that we get to a number between 0 and 24. So again, from the previous slide, that's our T number. We multiply it out, add 6.697, just doing the math for you here, and you get 524.7207754. Out of this, we need to subtract all the multiples of 24. So did that for you here. Turns out you have to subtract out 504. And you get that T0 is 20.7207754 hours. And in case anybody needs to know how you calculate that, this is how you do it. Okay, so now we have T0. We now need to get to our UTC date and time, which was 2 a.m. So what we do is we take the UTC time, 2 a.m., and we multiply it by this number here, 1.0027379909. SH just stands for sidereal hours, that you're wondering what that is. So we take T0 plus our SH, and that will give us Greenwich mean sidereal time at Greenwich. Again, our 2 hours here, the T0 we calculated on the last slide. Add them together. Well, first we have to calculate SH. Add that to our T0. And so Greenwich mean sidereal time is 22.72625512 hours in Greenwich on August 2nd, 2 a.m. UTC. Now, all we have to do is convert that to our local time, local star time. That's where your longitude is going to come into play. And you take the longitude, which way back at the beginning of this program, I showed you what it was at the Seminole State College Plaza. Divide it by 15, it gives you an H. Now, because we are west of Greenwich, England, so our stars over our head are going to be basically before the stars that they're seeing in England. We just have to subtract that. There's our longitude, there's our Greenwich mean sidereal time. This is our calculation of H, so we're 5.4 hours behind them. Subtract the 2, and we get that our local mean sidereal time is 17.30599652. If you take this fraction and figure it out into minutes and seconds, you get 17 hours, 18 minutes, 21 seconds. Now, what is this? If you were to go and look up star chart, every star chart will show you stars at within certain hours, and you can break that up into the minutes and into the seconds. So this actually tells you what star chart you would need to use to see what's up in your sky. If you have a planisphere, this helps you dial it into the right setting to show you the stars in your sky as well. So here's my favorite little planisphere that I like to use. This is actually a book that I learned from like ancient times ago, like late 70s, early 80s. And I had marked my map up with the sidereal hour time. So what this tells me is on August 2nd, around 2 a.m., I'm sorry, August 1st, 10 p.m., which is August 2nd, 2 a.m. in Greenwich, UTC. If I look south, I'm going to be seeing Scorpius directly in front of me, Sagittarius to its left, Ophiuchus above it. To my right in the west, I'll see Arcturus. I'll see Leo is setting, Virgo, Corvus on my left. Just rising in the east, I'm going to see the Summer Triangle. And if I look in the north, I'm going to see the Big Dipper to my left, the Little Dipper, Cepheus or Cepheus. Cassiopeia is just rising in the north. So knowing that star time really gives you a good sense of what's going to be up in the sky at any one time. So here's that DIY chart I told you about. If you want to use this for any other month you're observing and want to calculate your star time at the time you're observing, you can use this chart. For that celestial sphere image at the beginning, I used this book, To Know the Stars by Guy Otwell. Great little book. It's a simple guide to the night sky. You ever want to introduce somebody to astronomy and the concepts that we use, this is fantastic little book. This was the book that I learned from, but not this particular version. My book was like from 1980, like I said. Great star maps for beginners. To me, it's the best introduction to learning the constellations. Goes month by month, shows you what you're going to see in the sky. And that example was just 1 month, one particular month. All the calculations that I just showed you, I adapted them from this excellent book. Even gives you spreadsheets. You can just basically plug the date and time in, and it'll do all the calculations for you. But it also explains them. So you get 2 for the price of 1. That's it for this talk, but there's a sequel, which I hope to do in the fall, which is once you've calculated your local star time, that's kind of the key ingredient to actually calculate where exactly in the sky something is. So when you have your go-to telescope, these are the things that it's doing internally to say, oh, where do I point the telescope? So I'm going to briefly assume you figured out your local star time, and I'm going to pick some object. We'll figure out what object I'm going to choose, and we'll go through the calculation that says, okay, it's going to be at your compass direction 65 degrees, and it's going to be 35 degrees above the horizon, which is what your go-to telescopes do internally. So I hope you will be interested in that, and I will be presenting that hopefully in the fall for you. Thank you, and I'm done.
Thanks, John. Well, we'll be looking forward to that. Sidereal time is like astronomy 101. Anybody with a equatorial telescope trying to figure out when something is going to be visible, they need to have a good understanding of sidereal time. That might actually make another nice talk sometime to go into more depth about what it is and what it implies in your local horizon and things like that. For what time does Cygnus come up tonight? Well, what time is it in astronomy time, of course. So thanks very much. So next on our agenda is Mauricio, who's going to talk about an actual outreach event with actual people out under actual skies. It's July. The days technically are getting shorter. Really looking forward to when we can notice the days getting shorter later this fall. But apparently the weather gods were kind as well for the event. Mauricio, are you ready to jump in?
Yeah, I'm ready.
Okay. You're a little quiet.
Okay.
Yes, I can hear you, but you're a little quiet.
Can you hear me better?
You are louder now, yes.
Here we go.
Okay.
Sounds good.
I'm going to mute me.
All right. Okay, so yeah, yesterday we had our, it was called the Kodiak like Scout Leaders event at the Flaming Arrow camp down in Lake Wales. And yeah, I'm not gonna lie, on the drive over, my spirits were pretty low. I mean, I was seeing huge clouds, storm clouds, right in the direction I was heading to. But miraculously, as I was arriving, I was starting to see some blue skies, and we didn't exactly have a clear night, but it was clear enough that we actually went through a whole assortment of objects to show our group of about 15, 16 like young scout leaders. And some of the objects that we were able to see was the moon, M3, M4, M13. We did Saturn, actually. Eric caught Saturn at the very end of the night. That was pretty great. I was able to show people the Ring Nebula, which was fantastic. It was actually the best view I'd gotten it so far. And Eric had pointed out that the view of the Ring Nebula in my Celestron 8SE was huge. I had like a 10 millimeter eyepiece on it, and he was saying how unusually large and bright it looked. So I was really happy, and everyone got to see it like with almost no effort. So it was a really great night. And we were able even to see the Milky Way streaking above. We actually thought it was clouds at first, is actually how bright it was. So yeah, it's just a great example of, even when you have terrible weather, sometimes, you can get a little observing in as the clouds clear up. Eric, did you want to add anything?
No, it was good. It was good. It sure exceeded our expectations. And yeah, we got a bunch of things. M6, M7, M4, and Scorpius. Those open clusters. And I got to say the Ring Nebula that Mauricio had, I found it in my DOB and you could see it. But not only the size, but sometimes you increase the size of an object, a dim object. Ring Nebula is about 9th magnitude. The brightness and the intensity stayed there. It was just almost shocking how bright it was. Let's put it that way. You could not miss it. You could not miss it. So it was very well done. Very well done through the scope. And it was a great event. It was a great event.
Yeah, and I want to point out, if there's anyone sitting here at home who is feeling like maybe they're missing out a little bit on some of these events, to give you an idea of, during the pandemic, we've done this scouting event twice. Earlier this summer we went to a summer camp. It was like a Christian summer camp over. It was kind of close to where Lake Eustis would be, I think, out west. And reach out to Leonard Ward. He's our main outreach guy, and just let him know, hey, I want to be a part of these. Any event that might come up. I want to come and volunteer because I'm feeling cooped up. So just let them know, because we're always looking for volunteers. It's pretty much been me, Len, and Eric holding down the fort during the pandemic. But if you're jonesing to get out, let them know so you can shoot you an email next time there's an opportunity. I think there's one coming up, and we'll probably have. I imagine we'll have some outreach going in the fall. Hopefully, Richard, right?
I think it'll start accelerating actually as the school year begins, and then all the STEM nights start kicking in. Hopefully we'll be outrageously busy like we were a couple years ago before the pandemic.
So I'm excited about getting back to, like in September, and we're going to do an event at the college. The days are getting noticeably shorter, come the September timeframe. And we're also getting out of that rinse and soak cycle that we go through here in the summertime in Florida. So the odds of a good weather break, start improving as we get past that. So yeah, that'll be great. I'm jonesing to get back to that myself.
Absolutely.
Okay.
One last thing I would like to say before I started a new job recently. It's kind of thrown off just the way my weeks are structured. So I've kind of fallen out of the habit of keeping an eye on the weather, seeing when I'm going to go out and observe. But I would like to start getting back into that. So I'm gonna try and make an effort to kind of reach out in the groups IO or in the Facebook chat to see, who's willing to come out for when the weather's looking good. So just keep a lookout for that.
Sounds good. Thanks. I think this fall
thank you guys.
I'm going to get back to work on my lunar observing certificate, and I'm going to see if other people want to join me. And we could even do it virtual. We could have a list of objects that we all want to observe that night when the weather's clear, and we could work on it as a group. So speaking of the moon, next up is my minute on the moon. Let me share my screen, which by the time I get everything going ends up being closer to 2 minutes. But play. So here we are. This month's minute on the moon is going to be on the crater Schiller. Schiller is down along the southwestern portion of the moon, right above a darker spot that's right. It doesn't actually have an official designation. It's squarely right between the craters Schickard and Clavius, though. Schiller is a very unusual looking crater. Here we can look at it straight down from the Lunar Reconnaissance orbital data. And it has an elongated shape, even without the distorting effects of looking at it on the limb of the moon. It's 111 miles long and 44 miles wide, and has a lava-covered floor that's peppered with newer, younger craters. Schiller is elongated because it's actually formed by 2 to 4 other craters that all happened at about the same time and were joined together and ended up fused together all as one. Since you're not in orbit like the Lunar Reconnaissance Orbiter, this is what Schiller would look like to you in a telescope. Note the tiny little valley here. Let me point that out, little valley there, connecting with a little smaller crater off to the side called Rost B. And to the west, we don't have one central peak, but we actually have 2 central peaks that are kind of joined together in a sort of a central ridge there. This is further evidence that there was probably a little crater here and another crater here and another crater here, and they probably all hit at the same time. So it's probably a fragmented body that all landed in that way. So explore the mysteries of Schiller yourself. It will be in daylight on the moon from about July 20th until August 3rd this coming month. And that was just a minute on the moon. Now, Eric Hoin is going to spend several minutes on the sun. Take it away, Eric.
You got it. I hope to take it away. Let's see. There we are. Come on. There we are. How's that coming through?
Great. Sorry, I was on mute, so I
That's
would
okay.
interrupt. But yes, I see your slide.
I could see you motioning. I figured you were motioning with your hands. All right, this is good. And so change the title from 60 seconds with the sun, because I never left so little when I speak, to a few minutes with the sun. So viewing the sun, when we're going to talk about a little bit about what you see when viewing the sun. Structure of the sun, very simplistically. I've got a little illustration here. We have a core, we have a radiation zone, pretty self-explanatory, a convection zone, pretty self-explanatory. We have a photosphere, which we will talk about, a chromosphere, a corona, and we have sunspots. And the 2 items I'm going to talk about are highlighted in yellow. We're going to talk about the photosphere, sunspots. We also have granules and prominences on the sun. Usually what we're dealing with, a lot of folks in our astronomy society, and simple way to get started viewing with the sun is with a solar filter, which I will cover in future episodes. Especially like to do that in person with a demonstration of different filters. When we get back to the planetarium, I like to show the different filters. So the photosphere that we see, it's the outer surface of a star which radiates light. The origin of the name comes from the ancient Greeks, phos or photos meaning light, and sphira meaning sphere. So we have a light sphere, and of course our sun is one of those stars, or one of those light spheres in the sky. A photosphere, Sol's photosphere, approximately 100 miles thick. Temperatures, I converted it from Celsius to Fahrenheit for convenience, will run between 7,600 degrees and 10,300 degrees. And this image was taken, we'll talk about solar cycles here, during solar cycle 24, back on October 22nd of 2014. And I put this up for convenience so you get to see, of course, sunspots are numbered during the solar cycles, so numerically as they're forming. And for size comparison, a group of sunspots here, a size comparison between Jupiter and the Earth, so you can get in your mind's eye the size of sunspots here. So a sunspot the size of the Earth is not really that large. What are sunspots? Well, sunspots are temporary. And of course, what you see, they take place in the photosphere. Some of them will last for minutes, hours, days, weeks, sometimes months. Jeff Pettit had gone to Munich back in, I believe, 1999 to witness a total solar eclipse. And some of the sunspots and prominences as well were so large that when he came back to Orlando several days later, we observed with a hydrogen alpha and a white light filter, we observed those same sunspots and this one large prominence that was still there. It was just amazing, the duration of those. Sunspots, the sun releases heat through convection. We all know heat rises. Sun's got a lot of heat. And so the flux, or the constant change in the sun's magnetic field, it will inhibit the release of heat through the photosphere and create areas that are cooler, and we call those sunspots. Now, during an eclipse, you have a dark area and a lighter area, and same thing with sunspots. Now, you can see a lot of granulation, wonderful granulation here. We'll cover those later. But you've got a lighter area called a penumbra on a sunspot and a darker area called an umbra, just like during eclipses. Oh, okay, now what causes these sunspots also is, and has a lot of impact on them, is the dynamics of the sun, the magnetic field on the sun, and the magnetic poles. The magnetic poles will rotate around, and as they rotate around, and here's a little simple illustration, in alignment during solar minimum, when the magnetic lines interfere less with the dynamics of the rotation of the gas on the sun, you get solar minimums. During, as you move towards solar maximums, you can see as the magnetic fields change position, the magnetic poles change position, the rotating gas is interfered with by the lines of magnetism. And as you reach solar maximum, you've got a lot of interference from the magnetic field interfering with the rotating gas on the sun. Sun's magnetic field creates sunspot cycles. Periodically, 11-year change in the number of sunspots that we see in this photosphere. Now, the cycle can change in duration. Sometimes it's 10 years, sometimes 12 years. So they use 11-year cycle as a median for explanation of the sunspot cycle. And then you have a solar cycle, which on average is about 22 years long. So here's the last few solar cycles that you can see lasting about 20 some years each. Just finishing up with solar cycle 24. Now, sunspots are the longest continuously observed natural phenomenon. They've been observed since the 17th century. Before I go to the next slide, anybody know who came up with a telescope in the 17th century? I'll give you a hint. Early 1600s? I hear some of you. Of course, Galileo Galilei was the first to systematically observe sunspots in 1609. After, even though his first telescope didn't have any power, he was very enthusiastic about looking at sunspots, but made the mistake of trying to observe them directly. So it led to a lot of his blindness that he had. Macular degeneration. He had a brother named Michelangelo Galilei, and he had written that after observing the sun and seeing a few spots at one point during his observations, that for weeks thereafter he saw flocks of crows in his eyes. So he was systematically burning out his retinas, sad to say. but he began his observations in 1609. As you look at the chart here, you can see that, and if you can, well, you count them, okay, 24 cycles. And so you can see the maximum. All right, so maximum, really maximum. So maximums are not so great, like over 100 years ago, about 200 years ago. And during 1650, in the year 1700, there were very few sunspots. This was known as the Maunder minimum after Edward Walter Maunder, who really researched sunspots and kept track of this event. So you can see, even though you don't have more modern graph lines here of maximums and minimums, you can still see the work that was done, where you had some really good maximums take place in about 10-year periods here. So these, as far back as 1600, pretty accurate. Solar cycles, they're measured from minimum to solar minimum here. So where are we now? Where are we today? Sol's image for today. We have one noticeable sunspot here, number 2842. And this was taken by the Solar Dynamic Observatory, NASA's venture. And to give a real clear point, the latest sunspot cycles, okay. And I noted sun spotless days, not days with sunspots, but sun spotless days. So days when there were no sunspots. Take a look over at this 5-year span between 2011 and 2015, there were sunspots. Out of 5 years, there were only 3 days without sunspots. The rest were all had sunspots. Isn't that remarkable? So currently, as you're looking at the figures here, okay, we hit a minimum, say in 2019. Looks like maybe coming out of the minimum last year. And so if you go by percentages so far, we're getting towards a maximum here, where 24% of the days so far this year were without sunspots. And this was as of today. All right, so think about sunspots when you're observing. Have a good time, do it safely. We'll cover solar filters later, whether for astrophotography or just observing with your eyes, and have a great sol.
Thanks, Eric. We do have a number of solar astronomers or enthusiasts in the club. I know we have a growing number of people who have hydrogen alpha scopes or filters as well. And that's also another avenue for outreach for the daytime to do solar astronomy. I also want to do a quick, hey, Eric, you can quit sharing your screen, or can I turn you off? I don't know if you guys can see this or not. Here, I'll tell you what, I'll just share my screen. Do you want to continue? Yes. Yank. Unsolicited product review. Do you guys see the Amazon screen?
There you go.
On mine?
Yep.
Okay, good. All right. So really great book on fundamentals of solar astronomy that I picked up recently. I'm not finished with it by any stretch. But if you really want to get deep into solar astronomy, I highly recommend it. It's not super PhD level, but it's also not, super, magic school bus simplified sort of thing. So it's very accessible, but it digs into quite a bit of the science of solar astronomy. So while Eric was talking, I thought that might be a good little addendum there. So, okay, so that does though wrap up our July meeting. I'm just going to repeat a few things. First, thank you for the board and everybody who spoke and presented tonight. Thank you for your hard work. Thank you everybody in CFAS 2 who's been faithful through the pandemic. Very, very hopeful that come September, we can get back to meeting at the college We're a bit at their mercy as well as, the mercy of other things, but it'll be nice to get back together. We will continue to do some sort of electronic presence as well for people who can't make it in person, but that'll be great. Don't forget August. We're taking August off. The board's not taking August off. We're going to be hard at work planning a super awesome September talk. We may even spring for extra big cookies, that sort of thing. So I look forward to seeing you all then. Meanwhile, everybody stay in touch on Groups.io and keep an eye out for other announcements. And let me make sure I don't have not missed any messages or anything. Nope. So we're good. So everybody take care, stay safe, stay happy, and keep looking up. Bye.